The universe is full of whispers, strange, cryptic signals drifting through the vast emptiness of space, begging to be decoded. Among the most puzzling of these cosmic murmurs are the mysterious emissions from white dwarfs, the ancient remnants of dead stars. These dense stellar corpses should be silent, their fiery lives long extinguished, and yet they're not. Something, or perhaps someone, is making them sing. Signals pulse from these ghostly stars, defying explanation, leaving astronomers scratching their heads and rewriting textbooks. What if these aren't just random blips in the void? What if they're messages, clues, or even alarms from the far reaches of time and space? Imagine the scene: a team of scientists huddled over their instruments, their screens lighting up with patterns that shouldn't exist. The data is undeniable. White dwarfs, those fading embers of the cosmos, are broadcasting signals that ripple through the fabric of reality itself. Some pulse with eerie regularity, like a heartbeat from beyond the grave. Others flicker in chaotic bursts, as if trying to scream a warning across the light years. And then there are the ones that simply stop, vanishing without a trace, leaving behind only questions. What could possibly be causing these anomalies? Colliding dimensions, alien technology, or something even stranger, something we haven't dared to imagine yet? Tonight, we're diving deep into the enigma of white dwarfs and the 25 most baffling signals ever detected from these stellar ghosts. Each one is a cosmic riddle, a piece of a puzzle that could rewrite everything we know about the universe. Some signals hint at forces beyond our current physics, while others tease the possibility of intelligence lurking in the darkness. This isn't just about astronomy, it's about peeling back the curtain on reality itself, confronting the terrifying and thrilling possibility that we're not alone and that the universe is far weirder than we ever dreamed. So buckle up. By the time we're done, you'll never look at the night sky the same way again. The first signal that truly shattered expectations came from a lonely white dwarf drifting through the Cygnus constellation, a star that should have faded into cosmic silence millennia ago. Instead, astronomers caught it pulsing, not the erratic flickers of a dying ember, but a precise, rhythmic beat like a metronome ticking in the void. The pattern was too clean, too deliberate, matching no known natural process. White dwarfs cool slowly, their nuclear furnaces long spent, so what could possibly be driving these oscillations? The signal repeated every 1.37 seconds with terrifying consistency, a drumbeat from the grave that defied every model of stellar decay. Scientists scrambled for explanations. Some proposed unseen planetary debris, a shattered world spiraling into the white dwarf's gravitational grip, its death throes ringing the star like a bell. But the math didn't add up. The pulses were too regular, too pure. Others whispered about crystallized layers deep within the star's core, vibrating like some colossal tuning fork. Yet even that couldn't account for the signal's bizarre harmonics, overtones that stacked in ways no natural resonance should produce. Then came the wilder theories: microscopic black holes dancing in the star's heart, or vibrations from a higher dimensional shockwave rippling through our universe. But the most chilling possibility: the signal wasn't natural at all. Its structure bore eerie similarities to engineered pulsars, hypothetical beacons some theorists argue could be used by advanced civilizations to mark territories or transmit warnings. Was this white dwarf somehow repurposed, its corpse turned into a cosmic lighthouse, or was it something else entirely, a phenomenon so alien that our science simply lacks the vocabulary to describe it? One thing was certain: the universe had just handed us a riddle wrapped in starlight, and the answer might change everything. Among the first theories to emerge was the idea of exotic matter, an unknown form of material lurking within the white dwarf's core, warping its behavior in ways our physics can't yet predict. Some researchers speculated about strange quark matter, a dense, ultra-stable state where particles dissolve into a soup of free-floating quarks. If pockets of this bizarre substance existed inside the star, they might generate rhythmic tremors as they shifted under unimaginable pressures. But here's the catch: no lab on Earth has ever produced or observed quark matter directly. It's purely hypothetical, a mathematical ghost in the equations of particle physics. Without concrete evidence, this explanation crumbles into wishful thinking. Then came the gravitational lensing hypothesis. What if the pulses weren't coming from the white dwarf itself, but from something behind it? A massive object, perhaps a rogue black hole or a dark matter clump, could bend the star's light like a cosmic magnifying glass, creating the illusion of pulses as its gravity twisted the starlight. The problem: gravitational lensing usually distorts light in chaotic, unpredictable ways, not the crisp, metronomic beats observed. Even more damning, follow-up observations found no trace of a lensing object in the vicinity. The star's neighborhood was eerily empty, devoid of any hidden giants that could orchestrate such a precise illusion. Another camp pointed to magnetospheric interactions, the idea that the white dwarf's intense magnetic field might be trapping and slingshotting charged particles in a rhythmic dance. Neutron stars, the denser cousins of white dwarfs, are known to emit regular pulses this way, but the signal from this star was orders of magnitude weaker than any pulsars, and its magnetic field, while strong, wasn't nearly powerful enough to produce such effects. The numbers refused to cooperate, leaving this theory stranded in a dead end. The most haunting possibility lingered in the shadows. What if the signal wasn't astrophysical at all? Radio interference from Earth-based sources, satellites, military radar, even malfunctioning microwave ovens, has fooled astronomers before. But when researchers cross-referenced the signal with known artificial sources, everything came up clean. No human technology matched the frequency, the location, or the bizarre harmonic structure, unless someone had secretly parked a hyper-advanced transmitter in deep space. This wasn't our noise. Each hypothesis flickered like a candle in a storm, briefly illuminating a path before being snuffed out by contradictions. The truth remained locked away, somewhere between the known laws of physics and the vast, uncharted wilderness of cosmic possibility. Whatever was causing these pulses, it defied not just our answers, but the very frameworks we used to ask the questions. While the rhythmic pulses of the first white dwarf left astronomers baffled, the second signal tore through the silence of deep space like a scream in the night, sudden, violent, and then nothing. Nestled in the Andromeda galaxy, 2.5 million light-years away, a once dormant white dwarf flared to life in an explosion of energy so intense it briefly outshone its entire galactic neighborhood. Telescopes caught the burst in real time, a blistering flash of X-rays and radio waves lasting just 37 seconds before vanishing as abruptly as it appeared. No fading ember, no gradual decline, just a single, deafening cosmic shout swallowed by eternal silence. This wasn't just unusual, it was supposed to be impossible. White dwarfs don't explode twice. They're the quiet end stage of stars like our sun, cooling over billions of years into dark cinders. Yet here was one that had already died and then somehow found the energy to scream. The event shattered decades of stellar evolution models, leaving theorists scrambling. Some proposed a runaway nuclear chain reaction, where lingering pockets of hydrogen reignited in a suicidal frenzy. Others hypothesized a cataclysmic collision with an unseen object, a rogue planet, or a wandering black hole triggering a final, desperate burst of light. But the data refused to cooperate. The energy signature didn't match known stellar detonations, and no debris field or shockwaves were detected in the aftermath. The location made it even stranger. Andromeda is our closest galactic neighbor, meticulously mapped and studied. If white dwarfs could erupt like this without warning, why hadn't we seen it before? Worse yet, could our own Milky Way host similar sleeping giants, primed to erupt without precedent? The implications were chilling. A nearby event of this magnitude could fry planetary atmospheres or bathe entire star systems in lethal radiation. Then came the most unsettling detail of all. The burst spectral lines contained anomalies, chemical fingerprints that shouldn't exist in a white dwarf's atmosphere. Traces of heavy elements arranged in patterns that defied natural nucleosynthesis. It was as if something had tampered with the star's core, injecting foreign matter before it detonated. One radical paper suggested it might even be evidence of stellar engineering, a failed experiment or a weaponized celestial event. But with just one fleeting signal to study, the truth remains maddeningly out of reach. Whatever screamed that day in Andromeda took its secrets with it, leaving behind only echoes and a sky full of new fears. This explosive signal didn't just defy expectations, it tore up the textbook on stellar evolution. White dwarfs are supposed to be the universe's quiet retirees, stars that have burned through their fuel and settled into a slow, silent fade. But this outburst, it was like catching a corpse mid-sentence, shouting secrets we weren't meant to hear. The implications sent shockwaves through the astrophysics community, forcing a reckoning with everything we thought we knew about how stars die and what might lurk in their ashes. At the heart of the debate is a fundamental question. Could white dwarfs harbor hidden reserves of energy, some volatile fuel source we've overlooked? Mainstream models assume these stars exhaust their nuclear material before collapsing into dense embers, but the Andromeda event suggests otherwise. One radical theory proposes that under extreme pressures, white dwarf cores might form exotic isotopes, unstable elements that could spontaneously ignite, like a cosmic landmine waiting to detonate. Other researchers point to dark matter annihilation, speculating that if dark particles accumulate in a white dwarf's core over eons, their collisions might unleash sudden bursts of energy. The problem: both ideas require physics beyond our current understanding, stepping into realms where theory blurs into speculation. Then there's the timing. White dwarfs cool predictably over billions of years, their temperatures serving as cosmic clocks. But this explosion happened long after its host star should have been cold and inert. It's as if a stopped watch suddenly chimed midnight. Some astronomers argue this points to external triggers, perhaps a stealthy stellar companion, a neutron star or black hole orbiting unseen, periodically siphoning material until the white dwarf reaches a breaking point. Yet searches for such partners came up empty, leaving the trigger mechanism a mystery. The most unsettling possibility: this wasn't a fluke. If white dwarfs can erupt long after death, our galaxy could be dotted with dormant time bombs. Surveys now scour ancient star clusters for similar events, racing to determine whether this was a cosmic outlier or a terrifying new class of phenomenon. Until we know for sure, every flicker from these stellar ghosts carries a chilling question. Was that last pulse a farewell, or a prelude? The third signal haunts astronomers like a half-heard whisper, a faint but unshakable pulse radiating from a white dwarf nestled in the heart of the Orion Nebula. Unlike the violent outbursts or rhythmic ticks of previous anomalies, this one arrives like clockwork, repeating precisely every 47 hours. The pattern itself is strange enough, but the real mystery lies in how it changes. The signal modulates in a way that mirrors artificial transmissions, its frequency shifting subtly but deliberately, almost as if carrying information. Natural cosmic phenomena don't behave this way. Stars don't whisper in code. When researchers first isolated the signal, they assumed equipment error. Instruments were checked, recalibrated, checked again. Yet the whisper persisted, its 47-hour cycle unwavering. The modulation followed a complex but repeating sequence, peaks and dips in intensity that bore an eerie resemblance to pulsed radio signals used in human communication. Even more unsettling, the signal's bandwidth was unnaturally narrow, focused like a laser beam compared to the broad, messy emissions of typical stellar activity. It was as if someone or something had fine-tuned this transmission for maximum efficiency across interstellar distances. Theories erupted like supernova. Could this be some form of natural maser effect, where interstellar molecules amplify radio waves in unpredictable ways? Masers exist in space, but they're chaotic, their signals smeared across frequencies. This was precise, almost polished. Others suggested interactions with a hypothetical debris disk, a ring of shattered planets or asteroids around the White Dwarf, its irregular structure sculpting the star's emissions into artificial-seeming patterns. But no such disk was detected, and even if it existed, no known physical process could explain the signal's meticulous timing. Then came the unavoidable question: was this deliberate? The similarities to human-designed signals were superficial but haunting. SETI researchers ran the pattern through algorithms designed to detect intelligent origin, and while no decipherable message emerged, the structure scored unusually high for non-randomness. One astronomer compared it to hearing a distant radio station, just clear enough to recognize as speech but too faint to make out the words. The White Dwarf's location deepens the enigma. Orion's nebulous clouds are stellar nurseries, bustling with young stars and protoplanetary systems. A dead star there is like a tombstone in a playground. If this signal is artificial, its creators would have had to place it there deliberately, or survive long enough to witness their own star's death and still manage to broadcast from its corpse. Either scenario chills the blood. Perhaps the most disturbing possibility is that we're hearing an echo. White dwarfs are stellar relics, often billions of years old. If this signal is a beacon, it may have been transmitting since before Earth formed, a message on endless repeat, waiting for someone to finally listen. Or worse, it might be the last gasp of a civilization that flared bright and vanished, their final act to turn their dying sun into a cosmic alarm bell. Until we crack its code, the whisper from Orion remains a riddle wrapped in static, and the universe holds its breath. The moment the Orion signal's odd modulation pattern came to light, SETI researchers dropped everything. Here was a transmission from a white dwarf, a dead star displaying characteristics that flirted dangerously with what they'd expect from an intelligent source. The narrow bandwidth, the precise timing, the repeating structure, it ticked multiple boxes on their checklist for potential artificiality. But before the hype could spiral, sober analysis began. SETI veterans know better than anyone. The cosmos loves to mimic design where none exists. Their first move: rule out every natural explanation before even whispering the word alien. One leading hypothesis points to magnetospheric interactions, complex dances between the white dwarf's intense magnetic field and charged particles trapped around it. Neutron stars create similar structured emissions called pulsars, their lighthouse beams sweeping past Earth with metronomic regularity. But white dwarfs aren't supposed to have the magnetic muscle for such precise signals. Unless perhaps this one is a rare breed, a magnetic white dwarf with fields trillions of times stronger than Earth's, warping its surroundings into unnatural-looking patterns. Yet even this explanation stretches known physics. The signal's modulation isn't just regular, it carries layered variations like a song with verses and a chorus. No natural pulsar behaves this way. Then there's the debris angle. Imagine a shattered planetesimal, a remnant from the star's violent past locked in orbit, its metallic fragments reflecting and refracting radio emissions like a celestial disco ball. As the debris spins, it could chop the white dwarf's natural emissions into artificial-seeming pulses. It's a clever idea, but observations find no dust, no disk, no wreckage large enough to sculpt such a clean signal. The star's environment is eerily pristine, deepening the puzzle. SETI's most tantalizing tools are their detection algorithms, software designed to spot non-randomness in cosmic noise. When fed the Orion signal, the results were provocative, not conclusive, but just intriguing enough to raise eyebrows. The signal scored high on tests for informational structure, though no decodable message emerged. One researcher likened it to finding an unnaturally smooth stone on a beach. You can't prove it was carved, but it stands out all the same. Here's the uncomfortable truth lingering beneath the data. We may lack the vocabulary to interpret what we're hearing. Human technology communicates in ways shaped by our biology and physics. An alien civilization, if one exists, might engineer signals using principles we haven't discovered yet. The Orion transmission could be the cosmic equivalent of a QR code, a message we're too primitive to scan. Or, as most scientists quietly believe, it's a freak of nature, a stellar quirk that only looks designed because we're programmed to see patterns even where none exist. The debate rages, but one thing's certain: this white dwarf has become a Rosetta Stone for astrobiology. Whether its whispers are natural or not, they're teaching us just how poorly we understand the boundary between physics and something else. Every new observation peels back another layer, revealing not just the mysteries of a dead star, but the limits of our own imagination. The Crab Nebula has always been a graveyard of cosmic mysteries, but nothing prepared astronomers for the signal that began pulsing from a white dwarf near its heart, a signal that seemed to answer itself. Every burst, every flicker of light or ripple of radio waves, repeated precisely 12 seconds later, like a ghost whispering its own echo. This wasn't just unusual, it was unlike anything ever recorded in the annals of astrophysics. Echoes in space aren't unheard of. Light bouncing off dust clouds or gravitational lensing can create delayed copies of signals, but those follow predictable, messy patterns. This was different. The delay was exact, the replication flawless, as if the universe had pressed rewind on a cosmic tape player. Theories erupted like solar flares. Could space-time itself be folding around this white dwarf, creating a natural loop that trapped its emissions? Einstein's relativity allows for such distortions near extremely dense objects, regions where gravity warps the fabric of reality like a heavy weight on a trampoline. If the star's immense gravity bent light into a closed path, emissions might circle back, arriving moments later as perfect duplicates, but the math is fiendishly complex. For this to work, the white dwarf would need a peculiar, lopsided gravitational field, something more twisted than standard models predict. Some researchers speculated about hidden companions, a neutron star or black hole locked in a tight dance with the white dwarf, its gravity acting like a funhouse mirror to create the echo effect. Yet searchers found no such partner, leaving the distortion theory dangling. Then came the wilder ideas. Quantum physics suggests that particles can briefly tunnel through barriers, appearing to exist in two places at once. Could the white dwarf's emissions be exploiting some macro-scale version of this phenomenon, existing in overlapping states before resolving into duplicate signals? Or worse, could we be detecting a glitch in the cosmic code, a flicker in the simulation some theorists argue we might inhabit? The 12-second delay defied Occam's razor, resisting simple explanations with infuriating elegance. But the most haunting possibility isn't about physics at all. Human communication systems use deliberate echoes, repeating signals to ensure they're received clearly across noisy channels. SETI-owned protocols recommend similar redundancy for interstellar messages. The precision of this 12-second loop feels engineered, as if someone or something designed it to be noticed. If that's true, the implications are staggering. Either we've stumbled upon a natural anomaly so rare it mimics intelligence, or the Crab Nebula is hiding something far stranger than a dead star, something that knows how to make the universe echo back. Science thrives on predictability, especially when it comes to stars. A white dwarf's temperature should be its death certificate, a straightforward readout of how much heat remains as it fades into the cosmic dark. But Signal 5 laughs in the face of that assumption. Nestled in the Lyra constellation, this particular stellar corpse is doing something impossible. It's emitting radio pulses hotter than its surface. Imagine touching a block of ice only to feel searing heat radiating from within. That's the level of contradiction astronomers are grappling with here. The data is undeniable. Spectroscopic analysis pegs this white dwarf surface at a cool 4,000 Kelvin, about the temperature of a smoldering coal. Yet its radio emissions scream with the energy signature of something 10 times hotter, as if a hidden furnace burns beneath its icy exterior. The laws of thermodynamics insist this can't happen. Heat flows from hot to cold, not the other way around. So what's really going on inside this celestial anomaly? One faction of researchers points to atmospheric layering, a hidden shell of superheated plasma cloaked beneath the star's cooler outer veil. On Earth, we see something similar with Venus. Its thick clouds hide a scorching surface, but white dwarfs aren't supposed to have such complex atmospheres. Their immense gravity crushes material into uniform density, leaving no room for layered structures, unless perhaps this one is accreting matter from an unseen companion, funneling fresh fuel onto its surface in violent, localized hotspots. The problem: no companion star or debris disk has been detected, and the radio pulses emerge from the white dwarf's core, not its periphery. Then there's the dark matter angle. Some theorists suggest this star could be a cosmic trap, its dense core capturing and annihilating dark matter particles, releasing pent-up energy that bypasses the surface entirely. It's a tantalizing idea, but with no direct evidence of dark matter's existence, the theory leans on speculation. Others whisper about quantum tunneling effects, where heat energy skips the star's surface entirely due to bizarre subatomic behavior. The math works barely, but it requires conditions so extreme they border on fantasy. The most unsettling possibility: we're witnessing a form of stellar camouflage. If an advanced civilization wanted to hide enormous energy output, whether for propulsion, computation, or communication, sheathing it in a cold outer layer would be a brilliant strategy. The concept isn't entirely sci-fi. Humanity's own stealth technology masks heat signatures, but scaled to a star, that's a leap even the boldest theorists hesitate to make. For now, Signal 5 remains a thermodynamic riddle. Every explanation either breaks known physics or invites whispers of something beyond it. One thing's certain: this white dwarf isn't just defying expectations, it's rewriting the rules of how dead stars behave, and in doing so, it's revealing just how little we truly understand about the universe's darkest corners. Deep within the binary system KIC 8462852, a white dwarf and its sun-like companion perform a cosmic dance, one that hides a mystery in the shadows. Every 38 days, the larger star passes in front, eclipsing its dense, dead partner. Routine stellar choreography, right? Except for this, the white dwarf only broadcasts its bizarre radio signals during these eclipses. The moment the companion star slides into position, the transmission activates like a switch being flipped. When the eclipse ends, silence, not a whisper. This isn't just unusual, it's as if the universe itself is playing a game of interstellar peekaboo, revealing its secrets only when certain no one's watching. Theories cascade, each more tantalizing than the last. Leading the pack is the magnetospheric tango hypothesis, the idea that the companion star's magnetic field briefly intertwines with the white dwarfs during eclipses, creating a temporary conduit for energy to escape. Think of it like two hurricanes merging, their combined forces channeling winds in unexpected directions. During alignment, these twisted magnetic fields might funnel the white dwarf's emissions into focused beams aimed fortuitously at Earth. But there's a flaw. These interactions should produce chaotic, splintered signals, not the eerie coherence observed. Then there's the planetary debris argument. Imagine a ring of shattered moons or asteroid fragments orbiting the white dwarf, normally invisible against its glare. When the companion star eclipses it, the sudden darkness might allow cooler debris to wake up, reflecting or refracting hidden radio emissions toward us. It's a cosmic version of how streetlights seem brighter when fog rolls in, scattered light suddenly becoming visible under the right conditions. Yet surveys find no trace of such debris, and the signal's pinpoint precision suggests something far more organized than space gravel. The darkest horse in the race, the idea that we're witnessing intentional concealment. Some theorists note that eclipses provide perfect timing markers. Natural synchronization points for any civilization wanting to hide transmissions in plain sight. By only signaling when its companion star blocks the view, the White Dwarf could be masking its activity from observers in other directions. It's the cosmic equivalent of whispering behind your hand, ensuring only the intended recipient hears. But here's the twist that keeps astronomers awake. The signals aren't just timed to the eclipses, they evolve. Each broadcast varies slightly, as if responding to some unseen variable. Temperature shifts in the companion star, changes in the binary orbit's geometry, or something far stranger, like an intelligence adjusting its message. The data refuses to settle into comfortable patterns. Whether this is nature's latest puzzle or something beyond current understanding, one truth emerges. In the darkness of these eclipses, the universe is clearly mouthing words. We just don't yet know the language. The idea of a debris disk swirling around this enigmatic white dwarf offers one of the most compelling and unsettling explanations for its eclipse-timed signals. Imagine a graveyard of shattered worlds, countless fragments of rock and metal left over from the star's violent past, orbiting in a vast, chaotic ring. As the companion star eclipses the white dwarf, its gravitational pull could stir this debris field like a spoon in a cosmic soup, triggering avalanches of material to crash onto the dead star's surface. These impacts would unleash torrents of radiation, precisely the kind of structured radio bursts astronomers have detected. Recent observations from the Atacama Large Millimeter Array add weight to this theory. Subtle distortions in the system's infrared glow hint at vast, unseen structures, perhaps a disk of cold dust just barely detectable at the edge of our instrument's capabilities. Computer simulations show how such a disk, when nudged by the companion star's gravity during eclipses, could funnel sporadic streams of matter onto the white dwarf's surface. Each impact would be a miniature supernova, a flash of energy as asteroids or moon fragments vaporize on contact with the star's unimaginably dense crust. But here's where the mystery deepens. If debris is falling haphazardly, why do the signals carry such eerie coherence? Natural impact should produce noise-random bursts with no discernible pattern. Instead, these pulses arrive with mathematical precision, their frequencies shifting in ways that mirror error-correcting algorithms used in human communications. One radical paper suggests the disk might not be chaotic at all, but engineered a vast alien megastructure designed to harvest energy or transmit data. Imagine a Dyson ring not around a living star, but a dead one repurposed as a cosmic antenna. Of course, nature often outpaces our imagination. Another camp argues we're seeing a never-before-observed form of resonant accretion. As debris spirals inward, magnetic fields or plasma waves could sculpt the infalling material into rhythmic patterns, like sand grains aligning in wind-driven dunes. It's a delicate balance. Too much debris and the signals would smear into noise, too little and there'd be no bursts at all. That this white dwarf sits perfectly in the Goldilocks zone feels either like miraculous luck or something far more deliberate. Perhaps the most haunting clue comes from the signal's spectral fingerprints. Embedded within the radio waves are traces of heavy elements, metals like platinum and iridium, materials typically forged in supernova or neutron star collisions. These shouldn't exist in such concentrations around an ordinary white dwarf. Their presence hints at a cataclysmic past, a planetary system torn apart not by gentle aging, but by a violent, perhaps artificial disruption. Whether this debris disk is nature's wreckage or something more purposeful, one thing is clear: this dead star isn't just whispering, it's screaming. Hidden in the constellation Ursa Major, a white dwarf emits a signal that doesn't just challenge our understanding, it flips it upside down. Literally, this dead star's radio waves are polarized to an extreme degree, their electromagnetic oscillations locked into a rigid, unnatural alignment that defies every known model of stellar emissions. Polarization isn't unusual in space. Magnetic fields can twist light and radio waves like a cosmic corkscrew. But this is different. The signal isn't just polarized, it's perfectly polarized, as if someone had filtered out every irregular ripple, leaving behind a beam of pristine, orderly waves. No natural process we've observed produces such clinical precision, and that's what makes Signal 7 a cornerstone of cosmic mystery. At the heart of the enigma lies magnetism. White dwarfs often possess intense magnetic fields, remnants of their chaotic stellar pasts. These fields can polarize emissions, but typically in messy, unpredictable ways, like a flashlight beam scattered through a swirling storm. The Ursa Major signal, however, is more akin to a laser. Its polarization so uniform it suggests a magnetic field structured with impossible symmetry. Imagine a bar magnet the size of a star, flawlessly aligned from pole to pole without the usual turbulence or warping. That level of order simply doesn't occur in nature, where magnetic fields twist, tangle, and fracture under the strains of stellar evolution. One theory points to an exotic quantum phenomenon called vacuum birefringence, where space itself acts like a prism under extreme magnetic force, filtering and aligning light waves as they pass through. Predicted by quantum electrodynamics but never observed at stellar scales, this effect could, in theory, explain the signal's purity. But the magnetic fields required would dwarf anything ever recorded, pushing the limits of what physics says a white dwarf can sustain. Even neutron stars, the universe's most powerful magnets, don't produce polarization this clean. Then there's the timing. The signal's polarization isn't constant. It oscillates in a slow, deliberate rhythm, cycling every 6 hours like clockwork. Some researchers suggest a hidden companion, perhaps a rogue planet or brown dwarf, could be perturbing the white dwarf's magnetic field as it orbits, creating periodic alignments. Yet deep surveys reveal no such object, and the signal's regularity is too precise for gravitational nudging alone. The most provocative explanation dances on the edge of impossibility: engineered polarization. Human technology already uses polarized signals for communication, filtering out interference to boost clarity across noisy channels. Could this be a scaled-up version of the same principle, a beacon designed to punch through the cosmic static? If so, the implications are staggering. Either we're witnessing a natural phenomenon so rare it reshapes our understanding of stellar physics, or Ursa Major holds something far stranger, a dead star repurposed into a cosmic transmitter, broadcasting in a language of perfect, polarized silence. Like a ghost slipping through the fingers of time, Signal 8 haunts astronomy with what it didn't do stay. For 3 years, the white dwarf designated LS2247 pulsed like clockwork, its radio emissions arriving every 19 hours with such precision that researchers set their watches by it. Telescopes around the world trained on this unassuming stellar remnant, mapping its every flicker, convinced they'd found a new benchmark for understanding magnetic emissions from dead stars. Then, without warning silence, no gradual fade, no distortion, no last gasp, just an empty frequency where a signal had been, as if someone flipped a cosmic switch to off. Theories about the disappearance spiral into the surreal. One faction argues for a cataclysmic stellar quake, an internal rearrangement of the white dwarf's crystalline core so violent it shattered the magnetic fields powering the emissions. Picture an earthquake splitting the foundation of a skyscraper, but scaled to stellar proportions. Trillions of tons of degenerate matter lurching suddenly, snapping the intricate magnetic structures that had channeled the signal for years. The math supports this. White dwarfs can crystallize as they cool, their interiors freezing into lattice structures under unimaginable pressures. A fracture in that lattice could explain the abrupt termination. But here's the catch. Such events should leave behind gravitational ripples or X-ray signatures, and not a single observatory detected even a whisper of disturbance. Others propose an even darker scenario: the white dwarf's encounter with an invisible predator. Rogue black holes, detectable only by their gravitational fingerprints, drift unseen through the galaxy. If one passed too close to LS 2247, its tidal forces could have shredded the delicate plasma structures near the star's surface, dismantling the engine behind the emissions without leaving a trace. It's the cosmic equivalent of a sniper's bullet, instantaneous, traceless, and utterly devastating. The problem: no other stars in the vicinity show gravitational anomalies, and rogue black holes of the required mass should warp the space around them noticeably over time. Yet the void where the signal once pulsed remains stubbornly empty. Then comes the most unsettling possibility: that we weren't just observing a natural phenomenon, but something reactive. For decades, SETI researchers have debated the zoo hypothesis, the idea that advanced civilizations might deliberately avoid contact, masking their presence until humanity reaches a certain threshold. Could Signal 8 have been an experimental beacon, shut down the moment its operators realized we were listening? The timing is uncanny. The signal vanished just as papers about its artificial seeming regularity began circulating in astrophysical journals. A coincidence, perhaps, but in a universe where white dwarfs aren't supposed to vanish their own voices, coincidences start to feel like clues. What lingers beyond the theories is the chilling reminder of how fragile our grasp on cosmic truths can be. 3 years of meticulous observation, petabytes of data, countless hours of analysis, all rendered meaningless by a silence louder than any signal. LS 2247 now floats inert in telescope logs, a cosmic question mark written in static. Whether its disappearance was natural or not, one lesson screams from the void: the universe doesn't owe us answers. Sometimes it simply takes them back. Signal 9 doesn't just defy expectations, it mocks them. Most cosmic radio sources emit at steady frequencies, their transmissions locked into predictable bands like cosmic radio stations. But this white dwarf, tucked away in the constellation Cassiopeia, broadcasts on a channel that won't stay still. Its frequency drifts erratically, sliding up and down the radio spectrum with no discernible pattern, as if the star itself is tuning an invisible dial. What makes this behavior truly baffling isn't just the drift, it's the speed. Natural frequency shifts in space usually unfold over hours, days, or even centuries. This signal, it leaps between frequencies in milliseconds, rewriting the rules of stellar physics in real time. At first glance, the phenomenon resembles pulsar glitches, sudden jumps in the rotation rates of neutron stars, caused by internal crustquakes or superfluid vortices breaking loose. But there's a critical difference. Glitches alter a signal's timing, not its frequency. The Cassiopeia white dwarf isn't just speeding up or slowing down, it's fundamentally changing the voice it uses to speak. The closest terrestrial analogy might be a singer whose vocal cords randomly shift between soprano and bass mid-note, a biological impossibility. Yet here, in the vacuum of space, it's happening. Quantum physicists have thrown their hats into the ring with a radical explanation: vacuum polarization. In this scenario, the white dwarf's immense magnetic field warps the quantum foam of space around it, creating ephemeral particle-antiparticle pairs that briefly alter the local properties of the vacuum itself. These fluctuations could act like a cosmic prism, bending radio emissions into different frequencies as they escape. It's a mind-bending concept that empty space isn't truly empty, but a seething quantum landscape capable of rewriting the rules of radiation. While the math holds up in theory, observing such effects at macroscopic scales would be unprecedented, shattering our understanding of quantum mechanics' reach. But another possibility lurks in the shadows: resonance tunneling. Imagine the radio waves trapped inside the White Dwarf's atmosphere, bouncing between layers of plasma like a pinball. Under certain conditions, these trapped waves could quantum tunnel through barriers they shouldn't overcome, escaping at frequencies determined by the chaotic interplay of magnetic and gravitational forces. It's as if the star's own interior is a hall of mirrors, distorting its cries for help into something unrecognizable by the time they reach us. Yet for all these elegant theories, one stubborn fact remains. No known natural process produces frequency hops this rapid or this extreme. The signal's behavior edges dangerously close to what we'd expect from frequency hopping spread spectrum technology, a method human militaries use to avoid jamming by rapidly switching transmission channels. Coincidence, maybe, but when a dead star starts broadcasting like a cosmic shortwave radio, switching bands faster than nature should allow, even the most skeptical minds pause. Whether this is physics at its most exotic or something beyond current paradigms, Signal 9 leaves us with an unsettling truth. The universe may be speaking in tongues, and we're only just beginning to learn the language. The cosmos thrives on contradiction, but nothing quite prepares you for Signal 10, an X-ray scream from a graveyard. White dwarfs are the universe's cooling embers, fading into darkness over billions of years as their heat bleeds into the void. Yet nestled in the constellation Virgo, one stellar corpse defies this fate. Designated G129-22, this white dwarf shouldn't just be cold, it should be frigid, a fossilized remnant with a surface temperature barely exceeding the warmth of a summer day. But telescopes tell a different story. Despite its icy exterior, the star blasts out furious X-rays, as if a supernova's heart still beats beneath its frozen crust. This isn't just unexpected, it's like finding a glacier that secretly burns with wildfire. The moment these X-rays were detected, the hunt for explanations began. Standard stellar models offer no answers. White dwarfs this old have no fuel left to generate such violent energy. One faction of astronomers points to accretion, the idea that the star might be siphoning material from an unseen companion or interstellar dust. But here's the catch: no debris disk or binary partner has been detected, and the X-ray signature doesn't match the messy, turbulent emissions typical of feeding stars. Instead, the signal is eerily clean, almost surgical in its intensity. This leaves theorists scrambling for darker answers. Enter the most electrifying hypothesis: dark matter annihilation. If this white dwarf has been drifting through a dense cloud of dark matter particles, their collisions in the star's core could release bursts of energy, like invisible matches striking against the walls of reality itself. The math is tantalizing. Dark matter doesn't interact with light, but it does feel gravity's pull. A white dwarf's incredible density makes it the perfect trap, capturing and crushing these hypothetical particles until they annihilate in flashes of X-rays. It's a cosmic whisper that could finally prove dark matter's existence, or expose gaps in our understanding so vast they rewrite physics. Yet even this radical idea stumbles when confronted with the signal's details. The X-rays pulse with a regularity that dark matter models struggle to explain, their rhythm too precise for random particle collisions. Some researchers suggest quantum vortices, whirlpools of superfluid matter in the star's core, could be converting gravitational energy into radiation through mechanisms we've yet to map. Others float the possibility of primordial black holes, microscopic relics from the Big Bang, evaporating inside the star like time bombs made of space-time. Then there's the unsettling alternative that we're seeing the aftermath of stellar engineering. X-rays are the universe's brute force communication tool, capable of punching through dust and gas that would scatter weaker signals. If an intelligence wanted to mark a location, or perhaps power something hidden in the dark, repurposing a white dwarf as a stealthy energy beacon isn't beyond imagination. The star's cold exterior would mask its activity from casual observers, while its X-rays could carry data or coordinates across the galaxy. What makes Signal 10 so unnerving isn't just the mystery, it's the implications. If white dwarfs can harbor such violent energy undetected, how many others are hiding in plain sight? Every flicker from these stellar ghosts forces us to confront an uncomfortable truth. The universe's rulebook might have chapters we haven't even glimpsed yet. Whether the answer lies in dark matter, unknown physics, or something beyond our current science, one thing is certain: G129-22 isn't just defying expectations. It's holding up a mirror to our ignorance, showing us how much of the cosmos still lurks in the shadows. Across the vast expanse of the cosmos, a pattern emerges, one so precise it feels deliberate. Scattered over 1,000 light-years, 11 white dwarfs pulse in eerie harmony, their signals locked into a shared rhythm like a cosmic metronome. Each star emits at a different frequency, yet their beats intertwine mathematically, forming chords of radiation that resonate across the void. It's as if the universe itself is playing a symphony, and these dead stars are its unwilling instruments. The odds of such alignment occurring naturally, astronomers calculate them at less than 1 in 100 million. Either we're witnessing the rarest coincidence in galactic history, or something or someone has orchestrated this stellar chorus. The sheer scale of the phenomenon defies easy explanation. The stars involved span a region of space larger than the Orion Arm, with no visible gravitational or magnetic links between them. No known force can synchronize objects so distant in real time, not unless it operates faster than light, shredding Einstein's relativity in the process. Yet the harmonics persist, their intervals matching the overtone series found in human music, perfect fourths, fifths, and octaves ringing through the radio spectrum. Some researchers suggest quantum entanglement on a stellar scale, where particles in each white dwarf's core remain mysteriously linked despite the light years between them. But quantum effects typically manifest at microscopic distances, not across interstellar gulfs. The moment you scale up the math to white dwarf proportions, the probabilities collapse into nonsense. Another camp argues for primordial vibrations, ripples in space-time left over from the Big Bang, still resonating through the cosmos like aftershocks from a titanic collision. These vibrations, they propose, might stimulate white dwarfs to pulse in unison, much like tuning forks struck by the same shockwave. The idea holds poetic appeal, but observations deliver a brutal rebuttal. The harmonic cluster emerged recently within the last century. Ancient light from these stars shows no trace of synchronization in their youth. Whatever's conducting this celestial orchestra, it's a new player on the cosmic stage. Then comes the unavoidable question: is this structure artificial? The harmonics mirror mathematical ratios found in human-made communication systems, where layered frequencies boost signal clarity across noisy channels. SETI legacy protocols even recommend similar encoding for interstellar messages. Yet the energy required to synchronize 11 stars staggers the imagination, equivalent to harvesting the output of a supernova and focusing it with perfect precision for millennia. If this is engineering, it's engineering on a scale that dwarfs Dyson spheres or planetary computing grids. Perhaps the most chilling clue comes from the cluster's geometry. Plot the stars on a three-dimensional map, and their positions align with nodes of a tetrahedral lattice, a shape revered by mathematicians for its efficiency in distributing energy. Coincidence unlikely. Natural structures in space tend toward disks, spirals, or random scatter. Ordered lattices are the fingerprints of design. Whether this pattern stems from hyper-advanced technology or a previously unknown law of astrophysics, one thing is clear: the harmonic cluster isn't just singing. It's spelling something out, and until we crack its code, the universe's grandest choir remains a riddle written in starlight. Gravity might be the invisible hand conducting this cosmic symphony, an unseen force threading these distant white dwarfs together through ripples in spacetime itself. The theory of resonant gravitational waves suggests that each of these stellar remnants could be vibrating in harmony with fluctuations from an ancient cataclysmic event. Perhaps a collision of supermassive black holes billions of years ago, sending shockwaves through the fabric of the universe that still resonate today. Like tuning forks responding to the same low-frequency hum, the white dwarfs might be echoing these waves, their dense cores acting as perfect receivers for vibrations too faint for our instruments to detect directly. The math is tantalizing. If each star's natural oscillation frequency aligns with a harmonic of the original wave, they could lock into sync across unimaginable distances, their pulses drifting into alignment over millennia. But there's a glaring hole in this elegant idea. Gravitational waves weaken as they travel, their energy dissipating like ripples fading in a pond. For these waves to remain strong enough to synchronize stars thousands of light years apart, the source event would need to dwarf anything ever observed, a collision of black holes so massive it should have left a glaring scar in the cosmic microwave background. Yet the sky shows no such wound, leaving physicists to wonder if an even stranger mechanism is at play. Enter the interstellar medium, the thin soup of gas and dust drifting between stars. Some theorists propose that this diffuse material might act as a cosmic conductor, transmitting electromagnetic shivers between white dwarfs. Imagine the galaxy as a spiderweb. Pluck one strand and the vibration travels outward, disturbing distant threads. If a supernova or gamma ray blast agitated the local medium centuries ago, the resulting pressure waves could have nudged plasma around these stars into identical rhythmic patterns, their magnetic fields amplifying the signal like antennas. Observations reveal faint filamentary structures linking some of the harmonized stars' tendrils of ionized gas that might serve as transmission lines for these ghostly pulses. Yet the most radical explanations lurk beyond conventional astrophysics. Quantum entanglement, typically confined to subatomic particles, might scale up in the extreme conditions inside white dwarfs. If their collapsing cores forged entangled particles during their violent deaths, these quantum links could persist, binding the stars in an invisible network where changes to one instantly affect the others even across light years. It's a staggering notion, implying that the universe maintains hidden connections defying spacetime's limits. While mainstream physics dismisses such macro-scale entanglement as fantasy, the harmonic cluster dares us to reconsider. Then there's the haunting alternative, synchronization by design. Human engineers use precisely timed signals to coordinate network cell towers syncing via atomic clocks, GPS satellites aligning their broadcast. Could this stellar chorus be a scaled-up version, a galactic-scale positioning system or communication grid? The energy required would be unfathomable, but so is the harmony itself. Whether the answer lies in undiscovered physics or something far beyond it, one truth remains: these stars aren't just singing together. They're proof that the universe still holds rhythms we've only begun to hear. Buried in the galactic halo, a white dwarf older than the Milky Way itself pulses with impossible vitality. Designated WDJ0414-0853, this ancient stellar relic should have faded into darkness eons ago, its energy exhausted, its light extinguished by the relentless march of cosmic time. Formed when the universe was barely 3 billion years old, this star is a fossil from the dawn of galactic history. Yet against all odds, it broadcasts a faint but unmistakable radio signal, a whisper of energy that defies every model of stellar aging. If white dwarfs are cosmic tombstones, this one is a tombstone that won't stop ringing. The numbers alone tell a story that shouldn't exist. At 10 billion years old, this white dwarf has cooled to a mere 3,500 Kelvin, roughly the temperature of a welding torch, laughably cold by stellar standards. Its remaining heat should only power weak thermal emissions, barely detectable across interstellar distances. But the signal we're picking up isn't thermal noise. It's structured, pulsing every 11 hours with the consistency of a neutron star. Theory suggests white dwarfs this ancient should be silent, their internal dynamos stilled, their magnetic fields decayed into insignificance. Yet this one crackles with activity, as if something inside it refuses to die. Astrophysicists are confronting two equally unsettling possibilities. The first hinges on crystallization. As white dwarfs cool, their carbon-oxygen cores are thought to solidify into crystalline lattices, cosmic diamonds the size of planets. This process releases latent heat, potentially providing energy for sporadic activity. But here's the catch: crystallization should taper off after a few billion years. For a 10-billion-year-old star to still emit structured signals, its core would need to be crystallizing in ways that defy known physics, perhaps forming exotic metallic hydrogen layers or strange quantum states that prolong energy release. It's like finding a candle that burns for centuries, its wax never melting away. The second possibility is darker and far more exciting. Dark matter, the invisible glue holding galaxies together, may be the culprit. If this white dwarf drifts through a dense cloud of weakly interacting massive particles, their collisions in its core could generate just enough energy to power the emissions. Each annihilation would release a whisper of radiation, collectively producing the observed signal. The math is tantalizing. Ancient white dwarfs in the galactic halo could serve as dark matter detectors, their flickering lights betraying the presence of this elusive substance. Yet even this elegant theory stumbles when confronted with the signal's precise periodicity. Dark matter interactions should be random, not clockwork regular. Then there's the elephant in the observatory. Could this be intentional? The star's age places its formation during the universe's early chapters, when the first hypothetical civilizations might have arisen. A 10-billion-year-old beacon, if artificial, would be the ultimate time capsule, a message in a bottle cast into the cosmic ocean long before Earth existed. The signal's simplicity argues against this, but as SETI researchers caution, we may lack the context to recognize design. An ultra-advanced society might encode information in ways indistinguishable from natural phenomena hiding in plain sight. What makes WDJ 0414-0853 so revolutionary isn't just the mystery, it's the timeline. This star challenges our understanding of how matter behaves over cosmic epochs, forcing us to reconsider what's possible at the edge of eternity. Whether the answer lies in novel physics, dark matter, or something beyond our current science, one truth is inescapable: the universe's oldest stars still have secrets to share. And they're not done whispering yet. The signal arriving from White Dwarf, a P879, isn't just strange. It's warped, as if the universe itself is stretching and squeezing the star's voice into a cosmic funhouse mirror. Every pulse it emits arrives scrambled, its frequencies violently stretched one moment and compressed the next, a phenomenon astronomers recognize as extreme Doppler shifting. Normally, mild Doppler shifts occur when stars move toward or away from us, their light subtly reddening or bluing like a passing ambulance's siren. But this is different. The distortions here are so severe they imply speeds exceeding 5,000 kilometers per second, enough to cross the continental United States in the blink of an eye. Either this white dwarf is hurtling through space like a bullet fired from some unseen cosmic gun, or something far stranger is twisting the fabric of reality around it. One explanation points to a runaway scenario. White dwarfs can be catapulted to extreme velocities during supernova explosions, ejected when asymmetrical detonations send their surviving cores careening through the galaxy. If a P879 endured such a traumatic birth, its current speed might explain the signal's wild fluctuations. But there's a catch. Runaway stars typically follow predictable trajectories, their paths traceable back to exploded parent stars. This white dwarf's backstory reveals no such origin. Its motion seems random, directionless, almost as if something invisible is yanking it back and forth. That's where the companion hypothesis ignites debate. Imagine a binary system where the white dwarf orbits something dark and monstrous, a black hole or neutron star locked in a lethal gravitational dance. As the white dwarf whips around its unseen partner, its signals would stretch and compress wildly, mimicking the erratic Doppler shifts we observe. The math supports this. Precise timing of the distortions suggests an orbital period of just under 9 hours, hinting at an invisible object roughly 7 times the Sun's mass tugging at the star. Yet exhaustive searches reveal no X-ray glow or gravitational lensing, the usual fingerprints of such hidden behemoths. If there's a companion here, it's not just dark, it's utterly silent. Then there's the quantum vacuum theory, a radical idea floating at the edges of astrophysics. Near incredibly dense objects, the quantum foam of space-time might churn violently enough to create localized distortions, bending light in ways that mimic Doppler effects. Picture a ship navigating choppy seas, its movements exaggerated by the waves beneath it. If a P-879 sits in such a turbulent pocket of space, its signals could be surf-riding these quantum ripples, their frequencies warped not by motion, but by the very fabric of reality flexing around the star. But the most unsettling possibility is deliberate manipulation. Doppler shifting is a fundamental tool in human communication. Satellites use it to stabilize signals, militaries exploit it to evade jamming. Could these distortions be engineered, a form of celestial encryption or a side effect of propulsion systems beyond our comprehension? The signal's shifts aren't entirely random. Buried in the chaos are repeating patterns, like a cipher waiting to be cracked. Whether natural or not, one thing is clear: a P-879 isn't just moving, it's screaming through the void, and the universe is bending its cries into riddles. For 53 years, astronomers catalogued white dwarf PSRJ 1942+2563 as just another silent ember in the cosmic graveyard until the day it woke up screaming. Nestled in the constellation Vulpecula, this stellar corpse had shown no unusual activity since its discovery in 1969, its radio signature flatlining into textbook dormancy. Then, on March 12, 2022, telescopes caught an outburst so violent it temporarily blinded 3 deep space observatories. For 17 minutes, the dead star blazed with radio emissions 1,000,000 times stronger than its baseline, pulsing like a lighthouse spun by madmen before vanishing back into silence as suddenly as it erupted. The event wasn't just unexpected, it was a direct challenge to everything we thought we knew about stellar death. Theories ignite like supernova in the aftermath. Leading the charge is the magnetic reconfiguration hypothesis, the idea that white dwarfs might harbor unstable magnetic fields capable of sudden, violent rearrangements. Picture Earth's poles flipping, but compressed into minutes rather than millennia and amplified to stellar scales. As the star's interior crystallizes over eons, pent-up magnetic stress could rupture its crust, unleashing tsunamis of plasma that twist magnetic field lines like rubber bands until they snap, releasing catastrophic energy. It's a compelling narrative, but the data holds a brutal contradiction. No white dwarf on record has ever exhibited magnetic shifts this abrupt. Typically, such changes unfold over centuries, not coffee breaks. Then there's the dark horse, accretion-induced revival. If a rogue object, a wandering planetoid or shredded comet, plunged into the white dwarf's gravitational well, its death spiral could have dumped enough fresh fuel onto the star's surface to briefly rekindle nuclear reactions. The resulting firestorm would ignite the star's residual atmosphere like gasoline, producing the observed radio flare. But follow-up observations delivered a knockout punch. No infrared glow from heated debris, no chemical traces of vaporized intruders. The star's surroundings were as pristine as a vacuum chamber, ruling out cosmic trespassers. The timing itself is suspect: 53 years of silence, then a precisely 17-minute eruption. Natural phenomena rarely adhere to such neat intervals. One radical paper suggests we might be witnessing stellar-scale piezoelectricity, crystallized layers in the white dwarf's core generating electricity under pressure like a quartz crystal in a cosmic watch. If stresses built unevenly over decades, their sudden release could explain both the eruption's brevity and its eerie precision. But the energy output dwarfs anything piezoelectric effects should produce, leaving physicists to wonder if an unknown quantum phenomenon is at play. Then comes the whisper no one wants to voice aloud. Was this a test? SETI archives contain decades-old proposals about using stellar remnants as galactic bulletin boards, encoding messages in sudden bursts of radiation visible across interstellar distances. A precisely timed, short-duration signal from a historically quiet star ticks multiple boxes for artificiality. The real terror lies in considering who or what might have waited half a century before deciding to speak. Whether the answer lies in exotic physics or something beyond our current science, PSRJ 1942+2563 has issued a challenge. The universe's dead might not be gone. They might just be waiting. Deep in the heart of the Vela constellation, a cosmic doppelganger is playing a dangerous game of disguise. Signal 15, dubbed the spectral imposter by baffled astronomers, shouldn't exist. It pulses with the rapid, clockwork precision of a neutron star, its radio emissions slicing through the void every 1.4 seconds like a metronome forged in the fires of a supernova. There's just one glaring problem. The object emitting these signals isn't a neutron star at all. It's a white dwarf, a stellar relic so fundamentally different in composition and behavior that this mimicking act defies every known law of stellar physics. Neutron stars and white dwarfs are both remnants of dead stars, but their similarities end there. When a massive star collapses, it can leave behind a neutron star, an unimaginably dense object where matter is compressed to the point that atomic nuclei dissolve into a sea of neutrons, packed so tightly that a single sugar cube's worth would weigh as much as a mountain. These cosmic powerhouses spin at dizzying speeds, their intense magnetic fields funneling radiation into beams that sweep across space like lighthouse beams, creating the periodic pulses we detect as radio signals. White dwarfs, on the other hand, are the quieter, fading embers of smaller stars like our Sun. They're still dense. A teaspoon of their material would weigh as much as an elephant, but they lack the extreme rotation and magnetic fields needed to generate the kind of rhythmic, high-energy emissions we associate with their neutron star cousins. Or at least they're supposed to. The discovery of Signal 15 forces us to confront an unsettling reality. Either this white dwarf is breaking the rules, or our understanding of these stellar remnants is missing a critical piece. One leading theory suggests the star might be hiding a dark secret, a stolen identity forged in violence. If this white dwarf once orbited a neutron star in a binary system, the neutron star's explosive death as a supernova could have ejected it into space while leaving behind traces of its influence. The white dwarf's magnetic field, twisted and amplified during this traumatic separation, might now be pulsing in ways that eerily echo its former partner's behavior. It's a poetic idea, a celestial widow carrying the ghostly rhythm of its lost companion, but the math is shaky. No known mechanism allows a white dwarf to sustain such neutron star-like activity for millennia after such an event. Another possibility plunges us into the realm of quantum anomalies. White dwarfs are thought to crystallize as they cool, their interiors forming lattice structures akin to diamond. Under certain extreme conditions, vibrations in this crystalline core might resonate with trapped electromagnetic waves, creating harmonic oscillations that mimic pulsar emissions. The catch: these vibrations should dampen over time, not persist with the unyielding precision we're observing, unless, of course, something is actively sustaining them, an external force or an internal engine we've yet to imagine. The implications of Signal 15 ripple far beyond a single stellar oddity. If white dwarfs can convincingly impersonate neutron stars, our census of these objects and our reliance on their signals to map the cosmos could be fundamentally flawed. Surveys identifying pulsars might inadvertently include these imposters, skewing our understanding of stellar populations and their distributions. Worse yet, if the phenomenon proves more common than we think, it could force us to revisit decades of astrophysical models, rewriting the rules of how stars live, die, and whisper to us from beyond the grave. But the most electrifying question lingers in the static. Why this mimicry? Nature rarely produces such precise coincidences without reason. Is this a fluke of physics, a loophole in the universe's rulebook? Or is there something purposeful in this deception, a cosmic breadcrumb left by forces or intelligences we're only beginning to glimpse? Until we crack the spectral imposter's code, it serves as both a cautionary tale and an invitation. The universe is full of actors, and not all of them are what they seem. The universe loves its violent dances, none more dramatic than the catastrophic merger of two white dwarfs, a death spiral so powerful it ripples the very fabric of space-time. But what if these stellar collisions don't happen in silence? Signal 16 whispers a tantalizing possibility. Some white dwarfs might scream warnings before they collide, their final hours marked by eerie radio emissions that echo through the cosmos like a countdown to oblivion. This theory took shape when astronomers noticed an unusual pattern. A handful of gravitational wave detections from LIGO and Virgo, signatures of distant white dwarf mergers, coincided with strange radio bursts archived in telescope data. These weren't the explosive afterglows expected post-collision. They were precursors, faint yet structured pulses arriving hours or even days before the mergers themselves. At first dismissed as coincidental noise, the correlation grew harder to ignore. One standout case involved a white dwarf pair catalogued as GW190521, their gravitational waves washing over Earth in 2019, while radio telescopes had recorded a fading sequence of millisecond pulses from the same patch of sky 36 hours prior. The odds of this alignment being random, less than 1 in 10,000. The physics behind these death throes is as brutal as it is beautiful. As two white dwarfs inch closer in their final orbits, tidal forces warp their surfaces into monstrous, asymmetrical bulges. These distortions strain their magnetic fields like rubber bands stretched to snapping, generating colossal electric currents that erupt as radio emissions. Picture two stars locked in a lethal embrace, their magnetic fields tangling into a cosmic Tesla coil, arcing energy into space with every shrinking orbit. The closer they spiral, the louder the signal screams until silence falls, and the gravitational waves announce their violent union. But here's the twist: not all merging white dwarfs broadcast these warnings. Only a subset of systems with intensely magnetized stars seem capable of producing detectable precursors. This selectivity deepens the mystery. Are we witnessing a rare fluke of physics, or is there some hidden order dictating which stars cry out before they die? Future observations could hold the key. Upgraded gravitational wave detectors like LISA, set to launch in the 2030s, will pinpoint white dwarf mergers with unprecedented precision. Pairing these detections with real-time radio monitoring might reveal whether precursor signals are the exception, or a universal phase in stellar doom we've just begun to decode. The implications ripple far beyond astrophysics. If these signals are confirmed as merger harbingers, they'd transform white dwarfs into cosmic alarm bells, offering advance notice of some of the universe's most energetic events. Imagine a future where telescopes swivel at the first whisper of a precursor, capturing the final moments of these doomed stars in vivid detail. But darker questions linger. Could some of the unexplained signals we've already detected be the last cries of long-dead white dwarf pairs, their mergers unseen but their warnings etched into static? And if so, what other secrets might they carry about the nature of gravity, the limits of magnetic fields, or even the fleeting traces of civilizations that once orbited them? Signal 16 isn't just a curiosity. It's a key turning in the lock of one of cosmology's most violent processes, offering a front-row seat to stellar apocalypses before they happen. Whether these precursors prove common or vanishingly rare, they've already done something extraordinary. They've given the universe a voice in its own destruction. And we're only just learning how to listen. Among the endless chatter of the cosmos, Signal 17 stands apart, not for its strength or strangeness, but for its uncanny resemblance to deliberate communication. Pulsing from a white dwarf in the Draco constellation, this transmission arrives in clustered bursts, its on-off cadence mirroring the rhythmic precision of Morse code. Short pulses, long pulses, pauses stretched with mathematical care. It's a pattern so methodical, even veteran astronomers catch themselves wondering, are we listening to a language? The signal structure is what sets off alarm bells. Natural stellar oscillations tend to be chaotic, their rhythms dictated by internal turbulence or magnetic storms. But the pulses repeat in groups of 3 and 5. A numerical sequencing found in everything from Earth's naval signaling protocols to the Fibonacci spirals of galaxies. Machine learning algorithms designed to detect artificiality flag it immediately, scoring higher for non-randomness than 99% of known cosmic phenomena. SETI teams have pored over the data, searching for the telltale redundancy of language-repeated phrases, syntactic loops, yet the message, if it is one, remains stubbornly opaque. Physics offers its own suite of explanations, each more inventive than the last. Leading the pack is the resonant vibration theory. As white dwarfs cool, their crystallizing cores can fracture like drying mud, sending seismic shudders through the star. These quakes might ripple through surface plasma, modulating radio emissions into pulsations that appear patterned without true intent. It's a cosmic illusion, the stellar equivalent of hearing a heartbeat in the hum of an engine. But critics pounce on the timing. The signal's intervals aren't just regular, they're efficient, minimizing wasted energy in a way that mirrors human-designed communication protocols. Then there's the accretion shuffle. If a stream of debris, say, a shattered asteroid or a cloud of interstellar dust spirals onto the white dwarf's surface at uneven intervals, the impacts could generate bursts spaced like drumbeats. Picture raindrops falling on a snared drum, random in theory, but under the right conditions, producing rhythms that fool the ear. The hitch, observations show no debris field around this star, and the signal's clarity suggests a precision no chaotic bombardment could achieve. But the most electrifying hypothesis lies at the edge of orthodoxy, magnetospheric speech. White dwarfs with extreme magnetic fields can trap and accelerate charged particles, their polar funnels acting like cosmic particle accelerators. Under rare conditions, these funnels might emit in discrete packets, their timing shaped by the star's rotation and magnetic geometry. The result, a signal so finely structured it borders on artifice. Nature, it seems, is a consummate mimic. Public fascination inevitably veers toward the extraterrestrial. The signal's numerical patterns echo linkos, a constructed language designed for interstellar communication, and its bandwidth eerily matches the waterhole, a quiet slice of the radio spectrum between hydrogen and hydroxyl frequencies, long championed by SETI as an ideal channel for cosmic hellos. Yet for all the allure of alien intelligence, the burden of proof remains steep. The universe is vast, and its ability to conjure false patterns is vaster. What makes Signal 17 so captivating isn't just the question it poses, but the mirror it holds up to our instincts. Humans are pattern-seeking creatures, wired to find meaning in randomness, a survival trait that fills clouds with faces and static with whispers. Whether this signal is a fluke of physics or a handshake across the light years, it reminds us, The cosmos speaks in many voices. Some are cries, some are songs, and some perhaps are conversations we're only beginning to understand. The Draco White Dwarf continues its broadcast, indifferent to our theories. Every pulse is a Rorschach test, revealing as much about our longing for connection as it does about the star itself. Until the code cracks or the silence returns, we're left suspended between two equally thrilling possibilities: that we've stumbled upon nature's most elaborate parlor trick, or that somewhere in the dark something is counting the spaces between its words. The hunt for dark matter has taken scientists to the strangest of places: supercolliders buried deep underground, vats of liquid xenon in abandoned mines, even sensors bolted to the International Space Station. But the most promising detector might have been hiding in plain sight all along: the silent, cooling corpses of white dwarfs. Signal 18 flickers from one such stellar remnant in the constellation Fornax, a whisper of X-rays that shouldn't exist, pulsing with a rhythm that aligns terrifyingly well with predictions about how dark matter might announce its presence. White dwarfs are nature's perfect dark matter traps. Their incredible density, a teaspoon of their material weighs as much as an elephant, creates gravitational wells so deep that passing dark matter particles, if they exist, would become ensnared like flies in amber. According to theoretical models, these trapped particles would eventually collide and annihilate, producing faint bursts of energy as they dissolve into gamma rays or X-rays. The Fornax signal matches this profile exactly. X-ray pulses with an energy signature around 3.5 kilo-electronvolts, a telltale fingerprint predicted for certain types of dark matter annihilation. The pulses aren't constant, they arrive in clusters, as if something unseen is periodically dumping fresh particles into the star's crushing embrace. Critics pounce on alternative explanations. Could this be residual accretion left over interstellar gas spiraling onto the white dwarf surface and heating up? The star's surroundings show no trace of such material, and the X-ray spectrum lacks the messy, broadband noise typical of feeding stars. Others suggest internal crystallization waves, shudders in the star's crystallizing core releasing pent-up energy. Yet these should produce softer X-rays, not the sharp, high-energy spikes observed. The dark matter hypothesis stubbornly fits too well to dismiss, though caution remains. If confirmed, this would be the first direct evidence of dark matter's existence after nearly a century of searching. What makes white dwarfs uniquely suited for this detective work is their simplicity. Unlike neutron stars or black holes, whose extreme environments create electromagnetic chaos, white dwarfs are relatively clean laboratories. Their predictable cooling curves act like cosmic timers. Any excess energy stands out glaringly against the steady fade into darkness. The Fornax signal does just that, its X-rays dancing above the star's expected thermal emissions like a campfire spark in a snowfield. The implications ripple far beyond astrophysics. If white dwarfs are indeed lighting up with dark matter's fingerprints, they could map the invisible scaffolding of the cosmos. These stars are scattered across the galaxy like buoys in a dark ocean, each potentially recording the density and flow of dark matter around it. Future telescopes tuned to specific energy bands might even trace the distribution of this elusive substance in 3 dimensions, revealing the hidden architecture of reality itself. Yet the greatest thrill lies in the signal's imperfections. It doesn't match dark matter models perfectly. The pulse intervals are slightly off, the energy peaks a tad too broad. These discrepancies might hint at something even richer, not just proof of dark matter, but proof that it's more complex than we imagined. Perhaps multiple particle types are annihilating, or the white dwarf's magnetic field is twisting the emissions into unexpected shapes. Either way, Signal 18 isn't just a clue, it's a doorway, and on the other side lies a universe far stranger than we've dared to dream. Some signals don't just travel through space, they wrestle with time itself. Signal 19 arrives from a white dwarf near the galactic center. its pulses stretched and warped as if heard through a cosmic echo chamber. Each burst takes twice as long to reach us as physics says it should, its rhythm slowed to a crawl by unseen forces bending the very fabric of reality. This isn't just a delayed message, it's a transmission caught in the gravitational quicks and of extreme time dilation, offering a rare glimpse into Einstein's relativity in action. The culprit, most likely an invisible monster lurking between us and the source, a rogue black hole drifting through interstellar space. Einstein predicted that massive objects warp spacetime like a bowling ball on a trampoline, and when light passes near them, it must climb out of this gravitational well, losing energy in the process. For electromagnetic waves, this energy loss translates to redshift, the stretching of wavelengths toward the red end of the spectrum, and a dramatic slowdown in perceived time. Imagine the signal as a runner sprinting up an endless hill, each step sapped by gravity's relentless pull until their movements appear frozen from afar. That's the nightmare this white dwarf's emissions are battling. Observing such extreme time dilation pushes astronomy to its limits. Normally, white dwarf pulses are so regular they rival atomic clocks, allowing scientists to detect even microsecond delays caused by orbiting planets. But Signal 19's distortions are orders of magnitude larger. Its once crisp millisecond pulses now smear across entire seconds, their structure warped beyond recognition. To confirm this wasn't instrumentation error, researchers employed a clever trick. They monitored pulses from other white dwarfs in the same galactic neighborhood. Every star checked out clean except this one, its signals persistently sluggish like a clock submerged in molasses. The implications spiral beyond a single black hole's influence. If these stealthy gravitational lenses are common, they could be skewing our measurements of cosmic expansion, tricking us into misjudging distances to faraway objects. Worse yet, they might hide in the blind spots between stars, warping signals from potential extraterrestrial broadcasts into unrecognizable mush. Time dilation could be the universe's ultimate censorship, stretching alien messages into whispers we dismiss as stellar noise. Yet within this distortion lies an unprecedented opportunity. By analyzing exactly how the pulses stretch, astronomers can map the black hole's mass and trajectory with eerie precision, a technique called gravitational tomography. Each warped pulse encodes information about the lens's shape, like shadows revealing the contours of an unseen hand. Already, calculations suggest the culprit weighs around 12 solar masses and moves at 700 kilometers per second, a speed hinting at a violent past ejection from some long-dead star cluster. The most haunting question lingers: what else might be hiding in these gravitational shadows? If one undetected black hole can bend a star's voice into slow motion, how many more are out there, twisting the cosmos into a hall of mirrors? Signal 19 isn't just a curiosity, it's a flare in the dark, illuminating how much of the universe remains unseen and how easily reality itself can lie. Signal 20 drifts through the cosmos like a whisper in an empty cathedral, a pale infrared glow emanating from a white dwarf where no such warmth should exist. While most stellar corpses fade predictably into the cold embrace of deep space, this anomaly in the constellation Scorpius clings stubbornly to heat, its infrared signature blazing like a dying ember in a field of ash. The readings defy all standard emission spectra for white dwarfs at this stage of cooling, suggesting something, or someone, is stoking the fires within this cosmic grave. The star's infrared excess isn't just unusual, it's geometrically impossible under conventional models. White dwarfs radiate residual heat from their cores as they cool, but that energy should escape uniformly, like warmth dissipating from a stone left in the sun. Instead, this star's infrared glow clusters in lopsided, shifting patches, as if hidden furnaces burn beneath its surface. telescopes equipped with mid-infrared sensors reveal structures inconsistent with any known stellar activity, twisted plumes of dust swirling in patterns that suggest recent violent upheaval. One leading theory argues for a cosmic collision. Perhaps a rogue asteroid or a shattered moon fell into the star's gravitational clutches, its debris now smoldering in a disk of superheated dust. But the math falters. The energy required to sustain such infrared output would demand a debris field far more massive than any observed, and the irregular distribution of heat defies the symmetrical rings typical of post-collision fallout. Then there's the crystallized core hypothesis. As white dwarfs age, their carbon-oxygen interiors solidify into lattice structures, essentially forming planet-sized diamonds. This crystallization releases latent heat, which could theoretically explain lingering infrared emissions. But the observed temperatures surpass even these models, and the patchy distribution of warmth suggests localized, almost deliberate energy release. Some researchers propose quantum vortices, whirlpools of superfluid matter in the star's core, might channel heat unevenly to the surface, creating hotspots that flicker like candles in a draft. Yet no known quantum behavior scales to such dramatic stellar effects, leaving the theory dangling at the edge of plausibility, the darkest horse in this race. Dark energy interactions. If this white dwarf sits at a node where dark energy density fluctuates, the mysterious force accelerating the universe's expansion might briefly leak into our dimension, depositing energy as it goes. It's a fringe idea, but the star's location near a galactic void, a region where dark energy's influence is thought to dominate, makes it uncomfortably plausible. But the most electrifying possibility lies in plain sight. Infrared is the universe's stealth mode, a bandwidth where advanced civilizations might hide waste heat or propulsion signatures. If this white dwarf's excess stems not from natural processes but from something buried within it, the implications shatter comprehension. Imagine a stellar engine, a Dyson swarm's discarded scaffolding, or even a tomb for technologies so vast they repurpose dead stars as their power source. The infrared ghost refuses to fit neatly into any box, and that's what makes it one of the cosmos' most tantalizing riddles. From rhythmic pulses defying stellar decay to infrared ghosts clinging to phantom heat, these 25 signals have rewritten the rulebook of white dwarf behavior, or revealed how little we ever understood in the first place. Each anomaly is a crack in the foundation of astrophysics, the harmonized chorus of 11 stars singing in sync across light years, the Morse code precision of a dead star's final broadcast, the X-ray screams of a billion-year-old relic that refuses to fade. Collectively, they paint a universe far stranger than our models predicted, where stellar corpses aren't just silent tombstones but active participants in cosmic mystery. What binds these enigmas together isn't just their defiance of expectations, it's their refusal to fit neatly into any single explanation. Some signals, like the time-dilated whispers from the galactic center, showcase known physics pushed to extremes. Others, like the polarized laser beam emission from Ursa Major, flirt with phenomena we've only theorized. And then there are those, like the Draco white dwarf's coded pulses, that dangle the terrifying possibility of something beyond physics as we know it. The true challenge isn't solving any one puzzle, it's admitting how many pieces are still missing from our cosmic jigsaw. This isn't just academic curiosity. Decoding these signals could unlock revolutionary technologies, from dark matter detection to quantum communication. Imagine harnessing the precision of a white dwarf's pulsations to navigate interstellar space, or tapping into crystallized stellar cores as quantum computers. The harmonics alone, mathematical ratios repeating across light years, could rewrite our understanding of universal constants. And if even one signal hints at intelligence, the implications would eclipse every discovery in human history. The next breakthrough won't come from a single telescope or theory, but from collaboration, scientists and enthusiasts alike piecing together clues across disciplines. That's where you come in. Maybe you've spotted a pattern in the Crab Nebula's echoes that everyone else missed. Perhaps you've theorized why the Andromeda White Dwarf erupted after millennia of silence. The universe's greatest mysteries often surrender to fresh perspectives, so drop your wildest ideas in the comments. After all, the next voice to crack these cosmic codes might not belong to a lab-coated researcher, it might be yours. Until then, keep looking up, the stars are whispering and we're just beginning to learn how to listen.